Hello 12 STEM, good day to you. In this video, we will talk about motion in 2D or projectile motion. Okay, so these are our learning competencies for this video presentation. Derive equations for projectile motion. Illustrate the parts of a projectile motion. Explain that projectile motion is two-dimensional or combination of horizontal and vertical motions. And explain that horizontal motion is uniform while the vertical motion is free fall. And at the end of this video presentation, we will solve problems involving projectile motion. So these are our learning competencies. Hopefully we could get all these learning competencies in this video presentation. Now let's have a review of uniform motion and uniformly accelerated motion. For the past week, we discussed about uniform motion. We are dealing with motion of objects with constant speed and zero acceleration. Well, we know that if an object has a constant speed, then its acceleration is zero. Okay? Now, if the object is uniformly accelerating, there is a constant acceleration, and we know, class, that the speed is either increasing or decreasing. And that's the meaning of the uniformly accelerated motion. Last week, we also discussed about free fall, and free fall is an example of a uniformly accelerated motion because all objects, class, regardless of mass, will fall at the same rate of negative 9.8 meters per second squared, just like what you see in this video, in this particular picture, that for every second, the speed of the object is increasing at 9.8 meters per second. Okay? Also, in this picture, there should be an indication that the speed is negative. So let's try to put negative symbols here. All right. So we know, class, that after 5 seconds, the speed of the dropped object is now 49.0 meters per second. Okay. Now, let's try to consider this. Okay. For letter A long jumper's velocity while sprinting along the runway can be represented by a horizontal vector. That means the sprinter is running horizontally. Now, once the jumper is airborne or when the jumper starts jumping, okay, the jumper's velocity at any instant can be described by the components of the velocity. The components of the velocity will be two. We have v sub x, the horizontal velocity of the sprinter, and v sub y, which is the vertical velocity of the sprinter, because that sprinter jumped. Okay, so there must be a consideration with the horizontal velocity and the vertical velocity of the sprinter. And this leads to a new kind of motion, a motion wherein we have a combination of the horizontal velocity and vertical velocity, or horizontal and vertical motion, called the projectile motion. And that's why in our learning competencies, we call this projectile motion as 2D or two-dimensional. Okay, consider this cannon, class. As the cannon is launched horizontally, it is also free falling at the same time. Okay, so when you launch the cannon at when you launch the cannon horizontally, okay, the blue dots here, okay, represents the horizontal component of the motion. Okay, while it is moving horizontally, okay, that object is also affected by gravity. Therefore, it will be pulled down by gravity and it will accelerate downward, just like you just simply drop an object or free fall. Okay, so in other words, in this particular given or in this particular picture, the cannonball is moving horizontally and moving vertically at the same time. Okay, both horizontal and vertical velocities are acting on the object. Okay, therefore it is moving forward while falling. And this is the characteristic, class, of a projectile motion, a form of motion where an object moves in bilaterally symmetrical parabolic path, and it always has two components, the horizontal and vertical components. It is very important, class, that you remember vectors, okay, and how to resolve the horizontal and vertical components of vectors, because we will apply our knowledge in vectors in solving problems involving projectile motion. Okay, so again, when we say projectile motion, the object is moving horizontally while it is being affected by gravity. Okay? And it always has two components, the horizontal and the vertical components. Let's try to see the bigger picture of projectile motion. Okay, we have the parts of the projectile motion. Number one, have the trajectory. I know you already heard these terms, most especially in news concerning ligaw na bala incidences, okay, or when police investigators are trying to investigate incidences like ligaw na bala, as I said, okay, they are trying to get the trajectory of the bullet, okay. We also hear the term trajectory in sports, okay, just like ball sports, or in athletics like javelin throw, discus throw, okay. We can see there that we can hear them saying the trajectory of the object, okay. Trajectory is simply the path that the object follows, okay, and it always follows a parabolic path, okay. Even if you try to imagine it, when you try to serve a ball, okay, the ball glass will go in a parabolic path, and that its trajectory, okay. Now, as the object travels the trajectory, or as the object traverses the trajectory, there are two kinds of distances covered, okay. You have the height covered and the horizontal distance. The height class is the vertical distance, okay, and the range, we call that as the range or the horizontal distance from the point of release, okay, horizontally to where the object has reached the ground. All right, so you always remember the parts of the projectile motion. And there are two cases involved in projectile motion. The first case is the object is launched horizontally. If we try, class, to put this thing in the Cartesian plane, the point of release for objects that are launched horizontally is 0 degree. Okay? Therefore, you launch the object at 0 degree. Okay? Or you launch the object horizontally. Okay, we have to identify the angle because it's very needed to resolve the x and y components. If you could still remember your vectors class, we need the angle to resolve the x and y components, just like the projectile motion. Okay, so when the object is launched horizontally, we consider that as case number one, or case number two, the object is launched at an angle. So consider this particular example. Let's say this is the point of release, and we put this in the Cartesian plane. Okay, this cannonball is launched at a particular angle. Let's say 30 degrees. Okay, let's say 30 degrees. Okay, so we know, class, that it will go upward and then reach a maximum height and then will go downward, increasingly adding speed at a constant rate of negative 9.8 meters per second square. But in case number one, you just simply launch it horizontally and let the gravity and the horizontal motion do their work. All right. So always remember this. Case number one, the object is launched horizontally. Case number two, the object is launched at an angle. In this video presentation, we will focus on case number one problems. Okay, so we will be solving problems involving case number one. But before we solve problems involving case number one, remember this, that free fall and projectile motion are both affected by gravity. Consider this picture, class. Okay? So the ball in red is free fall, it is just being dropped. Okay? While the ball in yellow is in projectile motion. Okay? So these two scenarios on the two balls, okay, are both affected by gravity. Okay, this is the question. Which will reach the ground faster? Is it the red ball or the yellow ball? Try to think about it. Which will reach the ground the fastest? Is it the ball, the red ball, or the yellow ball? If your answer is both, you are correct. Okay? Both of them will reach the ground at the same time. Why? because these two balls class, okay, are affected by gravity, and both of them will be accelerating at the same rate. As you can see here, class, the lines, okay, the lines indicate that they reach the same time. For this particular case, they will be able to reach the same distance at the same time. Therefore, the red one will reach the ground the same time with the yellow one. The only difference, class, is in projectile motion, there is an added horizontal distance. Okay? There is an added horizontal distance, but it's still freely falling. Okay? Remove that horizontal remove that horizontal component, or remove that horizontal velocity, then the object is just like freely falling. Okay? So we can actually see here, class, that the horizontal component is independent to the vertical component. It means the horizontal component works independently with the vertical component, although they are happening at the same time on the object. Okay? So while this yellow object is falling, this is also moving forward. Okay? Just like the ball in red, it's falling. It's in free fall. Okay? That's why we call projectile motion as 2D, or motion in two dimension. Okay? It is moving in the dimension of the horizontal component, and at the same time moving in the dimension of the vertical component. Alright? I hope that's clear with you. Now, remember, as what I said, the horizontal velocity is uniform, constant speed. That means the velocity, class, the horizontal velocity from the start to finish is constant. Let's say, class, the speed of this particular uh, ball, or the speed of the horizontal component, is initially 5 meters per second. Okay, when it reached the ground, its component, or the horizontal component, is still 5 meters per second. That means the speed, the horizontal speed, is not changing. It's constant. Okay, while the vertical velocity is uniformly accelerated, it's free fall. While it's going upward, okay, let's try to follow the trajectory. All right, that's the best that I could do. All right. While the object is going upward, its velocity decreases. Its vertical velocity decreases. Take note of the term that I use. The vertical velocity is decreasing as it goes upward. Okay. Now, when it reaches the maximum height, it will now go downward with an increasing, negatively increasing velocity. Okay, negatively increasing vertical velocity. Okay, let's try to repeat that. Okay, the horizontal velocity, class, is constant from start to finish. Okay, so that's why we call that as a uniform motion, constant speed. All right, while the vertical velocity, class, is decreasing as it goes upward. When it reaches the maximum height, its vertical velocity there vertical velocity there at the maximum height is 0, okay, until such time that it goes downward with an increasing vertical velocity. That's why it's very important, class, to resolve the horizontal velocity and the vertical velocity, the horizontal component and the vertical component. In other words, if we're dealing with horizontal velocity, then we just need to get the horizontal components of the velocity. If we're dealing with the vertical components, or the vertical velocity, then we're dealing with the vertical components of the projectile motion. Okay, it says here that the vertical component is free fall, so we treat it like a free fall. While the horizontal component is linear, horizontal uniform motion, so we treat it like a uniform motion. Okay, now, in other words, if the horizontal velocity is uniform motion and the vertical velocity is uniformly accelerated free fall, we can use the kinematic equations for free fall for vertical velocity and uniform motion equations for horizontal velocity. So we already discussed this kinematic equations for uniform motion and for uniformly accelerated motion and free fall. And before we solve for before we solve for the components, before we solve for problems involving projectile motion, it is very important for us to refresh how to solve for the components. Okay, let's say class we have an initial velocity. You try to kick the ball at a particular angle. Okay, this ball class will have its v sub y, or the vertical component, and v sub x, or the horizontal component. Okay, so if that's the case, class, we know that if we try to kick this ball, okay, it will try to move forward while moving upward. Okay, try to move forward, mhm, while moving upward. Again, try to move forward with a constant speed while moving upward. As you can see, class, the arrow is decreasing in length, indicating, class, that the velocity, or v sub y, is decreasing until such time that v sub y is 0 at the maximum height. Okay? Now, after this, the ball will continue to move forward while it is now being pulled by gravity downwards. And the arrow now is increasing in length because we know that the velocity is increasing in its magnitude. Okay? So, how to solve for v sub y? Then we simply use the formula v sine theta, and v sub x equals v cosine theta. Alright? I need to emphasize this particular formula because we will be using these formulas in solving problems involving projectile motion, although I'll be teaching you a shortcut, most especially when dealing with cases with projectile motion. Okay? Now, this is the summary of the equation, class, for the kinematic equation. For the horizontal component, the acceleration is 0. Why is it 0? Because the object's speed is constant. Therefore, it's not accelerating. Its acceleration is 0. While for the vertical velocity, as the object goes upward and as the object goes downward, its acceleration is g, or negative 9.8 meters per second squared. Okay, always remember that. Now, for the velocity, the initial velocity, okay, is v cosine theta for horizontal, okay, and the initial velocity, class, and anywhere v sub x, anywhere from the projectile, will be equal. That means the velocity, class, the horizontal velocity from the start is the same to where the object is found in the trajectory. Okay, so for example, class, you try to throw the object horizontally, okay, and v sub x is, say, 5 meters per second. Okay, your initial velocity, class, initial horizontal velocity, I should say, is 5 meters per second. Now, when the object is here, say v sub x, still your horizontal velocity is 5 meters per second. This is the meaning of this particular equation. Anywhere, class, okay, anywhere on the trajectory, the horizontal velocity will be constant. Okay, however, in the vertical velocity, okay, we try to apply the formulas or the kinematic equations for free fall. Okay, because we know, class, that the velocity initially, okay, is different when the object is being pulled downward by the gravity. We know, class, that the velocity is increasing downward. Okay, so we use the formula for v sub y. Okay, we want to solve for uh, the velocity of the object here. Let's say v sub y1. Okay, v sub y1 is different from v sub iy. Okay, and v sub y1 is different from v sub y2 because we know, class, that the object's velocity is increasing downward. Okay, so we use these formulas. Okay, or we use this particular formula. And now for the displacement for the range, okay, since this is uniform motion, we just simply use the formula v equals distance over time, okay, and solve for d. D is equal to v times t. But take note of the velocity that we will use. We will use v sub x, okay? Do not use the vertical component for the range because range is a horizontal component. Now, to solve for the vertical distance, since d class is affected by gravity, then we use free fall equations for d. We can use d sub y equals v sub I yd plus 1 half gt square, and 2g dy equals v square y minus v square yi. Alright? So this is the summary of the equations that we will use for projectile motion. Now, remember this. At any instance, the velocity of a projectile is given by this. If you could still remember the formula for the resultant, okay, v equals the square root of v squared x plus v squared y, and the angle class is equal to v sub y over v sub x, and let's get the inverse of the tangent function. For us to understand this one, let's say given the particular vector v, okay, let's say it's unknown class. It's unknown, but we know class that the horizontal component v sub x is 3 meters per second, and the vertical component is 4 meters per second. V sub y is 4 meters per second. Okay, we can solve for v, okay, by using the formula v square x plus v square y. Okay, so this is just simply a version of the Pythagorean theorem. The answer here is 5 meters per second. Okay, now if the given v is 5 meters per second, we can resolve for v sub x and v sub y by using the formula v cosine x for the horizontal component and y, or v sine theta for the vertical component. And the angle class, the angle is v sub y over v sub x. Okay, so that's 4 over 3 arctan. Okay, next, at the highest point of the trajectory, only the vertical velocity is 0. As I said, the horizontal velocity is constant even at the highest displacement, at the highest or the maximum height, the horizontal velocity will not change. Only the vertical velocity is 0. Okay, the horizontal velocity is still v sub ix. Thus, the velocity at the highest point is equal to v sub I x. The the horizontal velocity, yun yung tinutukoy dito. Thus, the horizontal velocity at the highest point is equal to v sub I x, while the vertical velocity is 0. And the acceleration at the highest point of its trajectory is g and not 0. Okay? So, having these concepts, we will now be solving problems involving projectile motion. Case 1, in which the projectiles are launched horizontally.